The dodecahedral group is the name we give to the group of direct symmetries of the dodecahedron, which is this very object that you've seen at the beginning of each program. And by direct symmetries, we mean the symmetries that can be realized by an actual motion in space. So we're not allowing any reflection, we're just restricting attention to rigid body motions that put the dodecahedron back into the space it originally occupied. For instance, a rotation like this. Well, we're going to prove that this group of direct symmetries is isomorphic to A5, which is the group of even permutations on 5 symbols. And the latter will allow us to prove an important result about the algebraic structure of A5 using the geometric structure of the dodecahedron. Well, let's get started. What exactly is its geometric structure, and how does it relate to direct symmetries?
Well, if you've done your homework, you should be pretty familiar with the geometry. You should have made a smaller version of this with the kit we sent you, and found that it's got 12 faces, 20 vertices and 30 edges. And you may have noticed that these come in pairs. The vertices come in opposite pairs, the faces come in opposite parallel pairs, and the edges come in opposite parallel pairs. The reason we're thinking of these as pairs is that that will help us determine the individual motions of the dodecahedral group. But before we look at them individually, let's first see how many of them there are. If we line up this bottom face on this pentagon, then that determines a fixed region of space occupied by the dodecahedron. And the question is, how many rigid body motions are there which put the dodecahedron back into this space it originally occupied? How many of those motions are there? Well, what we're really asking is, how many different orientations are there for a dodecahedron occupying this space? Well, we can choose any one of the 12 faces to sit on the base. And once it's sitting there, there are 5 different orientations it can take. So that's 12 faces times 5 orientations for each, makes a total of 60 distinct orientations for the dodecahedron. So the dodecahedral group consists of 60 elements, 60 direct symmetries. Now what are they individually? We'll find in fact that each element can be realized by a single rotation about a particular axis. And it turns out that the axes of rotational symmetry fall into just 3 geometric types. Those through pairs of faces, pairs of vertices, and pairs of edges. Through the midpoints of opposite edges, through opposite vertices, and through the midpoints of opposite faces. And these 3 are the only types of axes of rotational symmetry. Exactly 6 different axes of this type, 10 of this, and 15 of this, 31 altogether. But between them they account for all 60 elements of the group. That's because for some axes there's more than one angle of rotational symmetry. And that's what we're going to look at carefully now, the possible angles of rotational symmetry about each type of axis. And we'll take edge-type axes first.
Well, I'm going to use 2 models for this. This one's for reference to show the original orientation of this one, which is my working model, and has an axis through a pair of opposite edges. If I rotate about this axis, then the only way the dodecahedron is going to go back into its original space is when this edge is in its original alignment. So a full half turn will do it, but there's no other angle that will put it back into its original alignment. And clearly this symmetry has order 2, because if I do it twice, I get back where I started.
So, for each edge-type axis, the half-turn is the only non-zero angle of rotational symmetry. That gives us 15 distinct rotations, 1 for each axis, and each one has order 2. Of course, there's the 0 rotation, the identity E. That's 16 so far. Next, axes through opposite vertices.
Well, here's an axis like this, through a pair of opposite vertices. And this time, there are 2 non-zero angles of rotational symmetry. And you can see that very clearly if you look straight down the axis. Because you see, these 3 edges are equally spaced around the axis. So there's going to be 2 rotations that put them back into the same pattern. A third of a turn to bring the black edge to there, and minus a third of a turn to bring it to there. A third of a turn, and we are back in the space we originally occupied, and similarly, minus a third of a turn. And both these rotations have order 3, of course.
So we get a total of 20 distinct rotational symmetries about vertex-type axes, plus 1/3 of a turn about each of the 10 axes, and minus 1/3 of a turn about each. Next, axes through pairs of faces.
And this time there are 4 non-zero angles of rotational symmetry. Well, here's an axis like this through a pair of opposite faces. And the rotations are as follows. There's 1/5 of a turn, 2/5 of a turn, 3/5 of a turn, and 4/5 of a turn. Notice that 4/5 is the same as minus 1/5, and 3/5 is the same as minus 2/5. So we can think of these as coming in pairs. 1/5 and its inverse minus 1/5, 2/5 and its inverse minus 2/5. And each of these rotations has order 5.
So we get 24 face axis rotations, 4 angles about each of the 6 axes, giving a total of 60 distinct rotations. So, as claimed, each of the direct symmetries of the dodecahedron can be realized by a single rotation. In other words, the direct symmetry group of the dodecahedron is in fact its rotation group. And that's the first part of the program finished. We've classified the 60 elements of the dodecahedral group into 3 types of rotational symmetry plus the identity. We can now use this classification to prove what we promised at the beginning, that the dodecahedral group is isomorphic to A5. Here are the cycle types of S5, the group of all permutations on 5 symbols. And A5 consists of the 60 even permutations which have the cycle types on the left. Now, any isomorphism between A5 and the dodecahedral group would have to match the elements like this. The face axis rotations would have to map to 5 cycles, because isomorphism preserves order, and the 5 cycles are the only type which have order 5. Similarly, the 3 cycles have order 3, and the pairs of disjoint 2 cycles each have order 2. And in fact, if you count up the even permutations, you'll find that there are 24 of these, 20 of these, and 15 of these. So we've got just enough of each type. And the way we're going to construct an isomorphism is to show that each rotational symmetry actually permutes 5 things, and that the cycle types are these. The 5 things are in fact 5 cubes, which we're going to put inside the dodecahedron.
Here's one cube. The 8 corners of the cube are at 8 of the vertices of the dodecahedron. On this model, we've just drawn the edges of the cube. And you'll notice that each edge is a diagonal of one of the faces of the dodecahedron. There's 12 faces and 12 edges. Well, actually, you can do this in reverse. You can start with the cube, and taking a sort of gable roof structure like this, and if you put that on one of the faces of the cube, and if you do that on each of the faces, you get the dodecahedron back again. Well, that's one cube. Here we've got 2 cubes, the original cube, and we've superimposed a black dotted cube. Here's the version with just the edges drawn. And now you'll notice that we've got 2 diagonals on each face, one from each of the 2 cubes. Well, there's 5 diagonals on the face of on each of the faces of a dodecahedron because they're pentagons. For instance, here's what the diagonals look like on 3 of the faces. We've numbered them on this one. 1, 2, 3, 4, 5. So presumably we could use the other 3 diagonals to specify 3 more cubes. So let's go on adding cubes. Here we've got 3 cubes. The original 2, and we've superimposed now a checkered cube. Now we've got 4 cubes. The 4th one is a white one. It's getting a bit difficult to see what's going on, and it's even more difficult when we've got all 5 cubes. The last one is this one with the white dots on it. There is one feature you ought to be able to pick out, though. At the middle of each face, we've got a little dip where all the 5 cubes come in to meet one another. Here's what that looks like on the version with just the edges drawn. You get a pentagon in the middle of each of these faces, formed by the 5 edges of the cubes. Well, so that's our 5 cubes. Now we're ready to look at the rotations and see how they permute these cubes into each other's positions. Let's remind ourselves what sort of permutations we should expect from each rotation.
Let's look at vertex rotations first. We expect them to match up to the 3 cycles in A5. Now, a 3 cycle leaves 2 of the 5 symbols fixed and cycles the other 3. So we expect a vertex rotation to leave 2 cubes fixed and cycle the other 3.
Well, let's look at just 2 cubes first. Rotation about the axis through their common corners will in fact fix the position of these 2 cubes. And you can see that very clearly if you look straight down the axis, because a third turn is going to carry the black edges into themselves and the black dotted edges into themselves, like this. Well, the cube certainly moved, but the black edges are back where they were, so the black cube is back occupying the original space, and so is the black dotted one. And when a cube is back occupying its original space, then it corresponds to a fixed symbol. So we've got 2 fixed symbols, and what we want to do now is to see whether the other 3 cubes have been permuted in a 3 cycle, as we hope they have. Well, here, as a reference, are the 3 cubes, and on the working model here, we've drawn in all the diagonals on the 3 faces surrounding the axis. And what I want you to notice is this equilateral triangle formed by edges of the 3 cubes. We've got a white edge, a checkered edge, and a white dotted edge. And when I do my rotation about there through a third turn, the white's going to go to the white dot to the checkered, and the checkered to the white. We're going to get a 3 cycle in fact. Look. The white is where the white dot was, and so on. And if I do the inverse rotation, the rotation through minus a third of a turn, then that's also going to give a 3 cycle. And the same thing's going to happen whatever vertex I choose, because you always get 2 cubes meeting there, which are going to be fixed, and the 3 cubes, other 3 cubes, form an equilateral triangle with their edges, and they're going to be rotated into one another.
So, each vertex rotation does correspond to a 3 cycle. Now for the edge axis rotations. We expect these to correspond to pairs of disjoint 2 cycles. So we expect them to leave 1 cube fixed and permute the other 4 in pairs.
This shows up very clearly if you concentrate on the gable roof that surrounds the axis. On the reference model we've a copy of the gable roof, and on the working model you can see that it's the gable roof for the checkered cube. This central diamond here picks out the edges of the other 4 cubes, and if we do our half-turn rotation about the axis, then the checkered cube's going to go into itself because it's got a face perpendicular to the axis, and the white and white dotted cubes are going to be interchanged, and so are the black and black dotted cubes. There. The checkered cube is back where it was, the white and white dots have been interchanged, and so have the black and black dots. So we've got a pair of disjoint 2 cycles. And exactly the same thing happens if we look at any edge axis rotation, because we've always got a gable roof with a central diamond.
So, edge axis rotations correspond to pairs of disjoint 2 cycles. Finally, face axis rotations, order 5, we expect them to permute all 5 cubes in a 5-cycle?
Well, here's an axis through opposite faces. And for a 5th turn, cube 1 is going to go to where 2 is, 2 to 3, 3 to 4, 4 to 5, and finally 5 back to 1, a 5-cycle, like this. And the inverse turn will also be a 5-cycle, and so will 2 5th turn and its inverse. The cubes will just go round 2 places instead of 1. And the same thing's going to happen for any face axis rotation, because you've always got a pentagon formed by all 5 cubes in the middle of each face.
And that's the lot. We've proved that the 3 types of rotation permute the 5 cubes in 5 cycles, 3 cycles, and pairs of disjoint 2 cycles, all even permutations. So we can represent each rotation by whichever even permutation it produces on the cubes, including the identity, of course. Now, in order to establish that this representation, this mapping, if you like, is an isomorphism, we need to show that it's 1-1 and preserves combinations in the 2 groups. Well, we don't know yet that it is 1-1 because, for example, we might find 2 different face rotations which produce the same 5-cycle on the cubes.
Well, as a matter of fact, different rotations can't produce the same cube permutation, though it's not easy to see it geometrically. But luckily there's a very simple group theory proof. All you have to notice is that only the identity rotation produces the identity permutation on the cubes, because we've seen that all the other rotations move, some or all of them. Then we argue like this. Supposing f and g give the same cube permutation, then if we do g and follow it by the reverse of f, that's going to fix all the cubes. But only the identity fixes all the cubes. So f inverse g is equal to the identity, and it follows that f is equal to g. So different rotations produce different cube permutations.
So each permutation in A5 represents a single rotation. Therefore, we do have a 1-1 correspondence between the group of rotations and A5. More than that, if we combine 2 permutations in A5, that automatically tells us the combined effect of the rotations they represent, the combined effect of the rotations on the cubes. So our 1-1 correspondence preserves combinations in the 2 groups, which makes the correspondence an isomorphism as claimed. And that brings us to the real payoff. We can now use this isomorphism to study the group structure of A5. We're going to show that A5 is rather an unusual group. It's what we call a simple group. That means it has no normal subgroups, apart from the identity subgroup and the whole group. Right, how are we going to show that? Well, normal subgroups have to be unions of conjugacy classes. So that's what we have to determine first, the conjugacy classes of A5. Well, we know the conjugacy classes of S5. The 7 cycle types are the 7 classes. But the 4 classes comprising A5 need not be conjugacy classes in the subgroup A5. We'll see exactly what the conjugacy classes are by looking at them in the dodecahedral group, where we can interpret conjugacy geometrically.
Well, remember the definition of conjugacy. 2 elements f and g in a group are conjugate if there's some element k in the group, such that f can be written like this, which means you do k inverse, then g, then k, and you get f. Well, that's the definition, but what it means geometrically is that f and g are the same operation, but done in different places. You see, k inverse moves things around, then you do g, then you do k back again, so that's f, and it's the same as g, but done in a different place. For example, supposing f and g are half-turns about edge-type axes, then we expect them to be conjugate because they're the same operation, but done in different places. And if we take a direct symmetry that takes that axis into that one, k inverse, and then if we do g, and then we do k back again, then we have in fact realized f. So f and g are conjugate. And similarly, any 2 edge-type rotations are going to be conjugate because there's always a direct symmetry k inverse that takes any edge axis into any other one.
So, the edge axis rotations all lie in the same conjugacy class. And as always, the identity element has another class to itself. No surprises so far. Let's take vertex rotations next. The first question is, can we get from a vertex to any other vertex using a direct symmetry K inverse? And clearly we can. So, if the angles of rotation are the same, any two vertex axis rotations will be conjugate. They'll be the same operation, but done in a different place. So it looks as if the vertex rotations might fall into two conjugacy classes because there are two angles of rotation. But it turns out they're all in a single conjugacy class.
To see that, let's use the convention that clockwise rotation is negative. Then, if you look round the back while I'm rotating, you'll see that we're actually rotating anti-clockwise. So, a rotation through minus a third here is the same as a rotation through plus a third round here. They're the same operation, but done in different places.
So, the 20 vertex axis rotations can each be thought of as the same operation, rotation through plus 1/3 of a turn, about axes in 20 different places, 20 different vertices. So they're all conjugate to one another because we can get from any vertex to any of the other 19 using a direct symmetry. Now, what about face axis rotations? Well, clockwise rotation about one face is the same as anti-clockwise rotation about the opposite face. So, the 6 face axis rotations through plus 1/5 and the 6 through minus 1/5 can each be thought of as the same operation, rotation through plus 1/5, about axes at 12 different faces, and similarly for the plus or minus 2/5. So the 24 face axis rotations split into at most two conjugacy classes of 12 elements each, the 1/5 class and the 2/5 class. In fact, there's no way of merging these into one class because the angles of rotation are different, even allowing for reversing the axis. And that's got all the conjugacy classes of the dodecahedral group, and hence of A5, with this surprise that the 24 5 cycles split into two classes. The geometric reason for this is obvious. No direct symmetry K inverse can take us from 1/5 of a turn to 2/5. Algebraically, that just means you can't get from one class to the other using an even permutation K inverse. Now that would have been very hard to prove directly in A5, but geometrically it's been easy. And now that we know the conjugacy classes of A5, we can look for normal subgroups, which must be unions of conjugacy classes. Now, the order of any subgroup must divide 60 the order of A5. So we want to see whether any union of conjugacy classes has a number of elements which divides 60. Well, we've got to have the identity in any subgroup. And if we add a single conjugacy class to the identity, you can see we won't get a number of elements which divides 60. For example, 1 plus 12, 13, doesn't divide 60. And if we try adding any two conjugacy classes to the identity, or any three, we still won't get a number of elements which divides 60. For example, 1 plus 20 plus 12 is 33. So, no union of conjugacy classes has a number of elements which divides 60, except for the identity element and the whole group. So these two are the only normal subgroups of A5. A5 is simple, an important group theoretic result derived geometrically.